Hi, good morning everyone. As you can see, I'm away from England today, and whilst I'm traveling around the world, I started to think about symmetry. Now, symmetry is this funny thing here. If you don't know, it's basically this pattern of mirroring one part, another part, and it's everywhere in nature. It's everywhere around us. It's in humans you can see this part similar to this part, and so forth, and trees and birds. And I was wondering, can we teach machines to recognize symmetry in nature? And it turns out we can. I used Zoom Intelligence to do just that, and now I'm gonna teach you how to get coding with it. So let's get in the house and start to code. Right, so let's get started. Now, for this particular project, you will need open frameworks because we're gonna visualize images, and if you don't know what open frameworks is, this is their website. You just go to download and then it will show you what to do. I'm not gonna cover this. I'll assume you've got a working copy of open frameworks, and this is what you need in terms of C++ library. It's my DFO that you can just download. You can just copy it and oh, that's my phrase frozen. Open a new window. Go into your open frameworks. Open frameworks. Release whatever you downloaded it, and go into apps. Probably create a new folder or go into my apps, and inside there, as you can see, I've already got it. But you can basically just go into my apps and see the apps. See the apps where my apps is, and then just do git clone. Right. Once you do this, you will have the repos. So that's where we're gonna get started. Right. So once you download the repo, you will find this. Okay, you will find this. You will have the algorithm, the DFO algorithm, and you will have the examples in which one of them, image symmetry, is what we're interested in. Now, this is actually the second take of this video, and I've tried to live code a version of this from scratch. It took me 2 hours, even with notes on the ones that I've already built. And I thought, you know what, let's avoid this. Let's instead run through how I built this so that I can try and keep it very short and simple. And here is how it works. It's an open frameworks project. So it will run using OpenGL, and it's going to be a graphics project. And here how it works. We've got the open frameworks C++ structure. We've got OFUP CPP, which will set up the algorithm. This, by the way, is sorry, my dog in the background. This, and also sorry for the vents of my laptop, they are awfully loud, but this is a custom class that we've created, the DFO visual, which it's in here, and I've just created these two, header and CPP file. Everything else, the DFO comes with it anyway. That's the actual library, and this Worm Intelligence library, and then these variables here in the main OFUP are just variables I'm using to switch through, to switch image and to switch algorithm and things like that. So something just high level for the program to work, but not necessary for the algorithm and for the basic structure of the program. And then what I'm doing is I'm basically setting up this class so that it generates the swarm of the Swarm Intelligence, and it loads an image, and it then starts. It gets ready to do the checks and everything, and then I draw the flies, the agents, onto the picture. I visualize what they are and what they're doing, and then I visualize the best in the swarm, which hopefully is an indication of where a symmetry could be. And then I just drew a bunch of stuff. In particular, I'm drawing what the type of symmetry I'm looking at, and then I've used this sort of switch key press to switch across stuff depending on keys. So this is more like Open Frameworks things, and it's just to show you better through images without closing and opening the program. Nothing really to do with the algorithm. The algorithm's bits are setup, draw, and update. What happens with this? Well, when an object of this class is created, it spawns a DFO, which is this worm, and it contains all the logics behind the algorithm. And what DFO does, it creates loads of little agents, simple agents that are basically small programs that check with the function that you've got to pass in for a point in space, in an n-dimensional space. For this point, basically, if it fits if it fits a certain criteria and how much or how little, and then it returns a fitness value of this point. And not the highest actually, but the lowest the fitness, the closer the fitness is to 0, the better it is for the algorithm, until it minimizes it to 0, which ideally is a solution. It found what it was looking for, at least at that point. And at least using, at this stage of sort of checking, and it checks a lot of times, and each agent checks one bit, and it gets done over and over time. And everything else is just a few image variables that I use to draw, and a few strings and that I use again to draw, and then the constructor, and then a couple of functions like brightness to return the brightness of a point, and it's just a wrapper for Open Frameworks native get brightness function, and then Raptorus. It basically allows me to check near the margin of an image, and if I go beyond that, it will check on the other side, a bit like Pac-Man. You go up the top and you come out from the bottom. And everything else is again, sorry for my dogs, everything else is fine, I guess. Let's just go into the CPP definition. So what the algorithm does, it sets the dimensions to 2, because we're obviously in a 2-dimensional space, and every image has pixels that can only lay into a space which is 2-dimensional. So 2 dimensions. We constrain the algorithm to only search for positive values, because obviously an image will have values of pixels between 0 and width, and between 0 and height, and it will not have negative values. Then we load the image, and then we do some setups. Okay, so this setup, which is called by the main setup, it has a little subfunction here which wraps up a few settings. We get the pixel from the image, and we load them into an OFPixel object, which is basically an array of pixels with a few other funny things that Open Frameworks has for us. And we use then that later on to get the brightness of a pixel by checking the array and getting the color and the brightness. And then we get we set the search space width of each dimension of the algorithm to match the image, and then we store the width and height into 2 variables for just because it's handy. We set the frame rate to 10, otherwise the algorithm would go fast and you will not see what's happening. The flies will just jump all over the place. And we set the window shape to be equals the image plus a bit, because we want to display a few text, some text. Population size 50, so we've got 50 agents on the field looking for symmetry, and then we tell the algorithm, alright, the setup is done, generate a swarm, and launch this swarm onto the field. We've got 3 setups, they're exactly the same, except that 2 of them, this and this, are only looking for a horizontal or vertical symmetry. So What do I mean by that? Well, let's show you how this program works. We've got images that sorry for the vents, by the way, they're really noisy, but we've got images, okay, like this and like this. And what the algorithm is going to do is going to get a point, and this is the position of the agent, and then the agent needs to check against its position against a fitness function, which we'll have to set, and we will set in a way that this fitness function would say, right, I've got this point, let's choose a random x and a random y, and a random width, say this, and a random height, let's say this, and this is gonna be our second point, and then choose the point that mirrors that, so plus y plus x down here. Then with these 2 points, run for a patch that goes for, say, 50 pixel, 25 to the left and 25 to the right, and so in height. So you've got 2 squares, 2 patches, and you've got 2 patches that will have to be checked against each other. And then once it checks them against each other, it sees if these patches are the same, have the same brightness overall, that is, all the pixels are the same, or maybe different shape, but the chances are that if they are very similar in shape and color, if they're very similar things, you know, say this patch and this patch, then the value will be low, and then we'll have to and then we'll have a symmetry, or as close as we can to a symmetry. So we get, because every time we change the random x and y, you know, one time it's going to take a patch here and a patch here and a patch here, so the same fly might return a different fitness at each loop. And this is fine because we want to check for symmetries, and we want just indications of where symmetries might be. And it's fine if agents look for different axes of symmetry in different points. Obviously, the horizontal one and the vertical one are limited to these 2 axes, each on them. But there you go. There you have it. And this is how we set it up. We set up a margin. We set up variables, we set up everything that we need to run this algorithm, and this is the final bit. So this is basically what I just said in terms of defining the random points and then getting a patch and then comparing a patch to each other, and here we have it. So we can choose between the 2 versions of the algorithm. The yellow patch, by the way, the yellow point is just an indication of a point that had a really good fitness, and sometimes it's useful, sometimes it's just it gets stuck somewhere and doesn't move. To be honest, it's not the most useful thing ever. I put it there, but it's you can almost always ignore it. But what we can see is that how this worm is kind of clustering around points on this axis and on this axis, and this is exactly what we want. We want the algorithm to tell us, hey, look, at this point there is some symmetry. Now, it's not telling us which direction the symmetry is, although we can change that. You know, for example, this was looking for horizontal symmetries, which on this image is not exactly useful. But for example, this is looking for two-way symmetry. And two-way symmetry, what I mean by two-way symmetry is actually, I mean a change in angle symmetry, and it's just looking everywhere at any directions for symmetry, and it's kind of clustering, you see, around this area, because obviously as humans we can see there is symmetry there, and the algorithm is also seeing that there is some symmetry there. So let's move on. Let's see, for example, this image here, and it should cluster towards the center or near axis, because axes are symmetrical, and it is. You see, there is symmetry here, there is symmetry here, there is symmetry here, and it's always clustering in one of these lines, okay? Let's move on. This again is clustering around the center because these two sides are quite symmetrical, and this is clustering again around the center or around this area or around this area. And we've also got images like this. And as you can see, it's kind of clustering around this middle bit because you've got symmetry, obviously, on this side. But then if you change the angle, you don't have symmetry. So then the algorithm tries to look for other bits. And maybe because it looks at different scales, maybe there is some symmetry if you look at this patch, but there isn't symmetry if you look at this big. Now, I've also put a limit here. So actually, at the moment, I'm only checking for 400 by 400 patches of the image. If the image is smaller, it checks through the whole image. But other than that, for example, have a look here. We're showing that there is some symmetry in this part of the image, and the symmetry could be, for example, this and this, and now here in the middle, obviously the most evident, from this and this side. And again, this is a bit of a tough one. It's very confused and it keeps going around, but it kind of clusters. You see, like it seems like staying longer in areas where you can expect symmetry. Look at the zebra, how it's sort of very confused by having so many different ways of being symmetrical. But again, you see the nose is very attractive, and this side is very attractive, and this side is very attractive, and my dog keep barking. But there we go. This is the symmetry algorithm, and you can just download it, play around with it, ask me any questions about it, and I'll be happy to answer them. From Francesco, this is it for today. Thank you very much for watching, and I'll see you next time. Bye bye.